Hello, everybody. Today we are starting on a new layer. Remember, as this little recap shows, the applications layer took a message from a client to a server, from one app to another. Then the applications layer passed that message to the transport layer, usually TCP or UDP, and that transport layer took the message from the host it was on to the destination host. At the destination host, the message was passed up to the application layer at that host. The network layer, which we just finished, is concerned with routing and works at all nodes along a path. So the transport layer sent its message to its network layer at the source host. That network layer connected to the next node in the path, and that next node connected to the next node, and so on, until they got to the network layer of the destination host, and then it went back up to the transport layer and to the applications layer. Now we are looking at the data link layer. This one is very interesting. There's a lot of things going on here, including a lot of error detection. The data link layer is the layer which handles our access to the network connection. It will essentially take things from the network layer and move them along. Now we talk not about packets, which we were talking about at the network layer, but rather about datagrams. And a datagram is carried in a frame. Now, there's one layer below this in the TCP/IP model. That's the physical layer. Usually in this course, we don't do an awful lot on the physical layer. We'll mention some parts of it, but we don't spend a lot of time talking about how to encode bits. Maybe I should. Maybe I'll have time to talk about it later, but I doubt it. Now, the bottom three layers of the node are sort of a problem. Instead of being very distinct, they are usually handled by an Ethernet chip. So they all go on one chip. Ethernet is a very interesting protocol. It developed from a PhD thesis, which was unusual for something like that to happen. And it's become the way that local area networks talk to one another. And it covers, as I said, the bottom three layers of the TCP model, TCP/IP model, pardon me. We've talked a lot about requests for comments, RFCs. I've shown you some. You've looked at some in the homework. When we get to this layer, we're no longer talking about RFCs, although they may be there. The real important group now is the IEEE. IEEE is the Institute for Electronic and Electrical Engineers. It has, I think, around 100,000 members or more. It's the largest of the groups, professional groups like it. It's larger than ACM, which is the Association for Computing Machinery, and the Internet Society. The IEEE is huge, and IEEE has defined some standards. The one that is most important to us is called the IEEE 802. The IEEE 802 defines how local area networks work. And the way it does it is there's a set of subcategories. They're all 802 point something. The earliest one started at 0.1 and 0.2. 802.3, for example, is basically Ethernet. It may have a few slight wordings different, but it's basically Ethernet. 802.11, you notice it's getting further up, so it was done later, is Wi-Fi. 802.15.1 is Bluetooth. And 802.16 is WiMAX. This is the place where things are happening now. The higher 802s are moving along. We're going to talk a lot about local area networks. We're on one. The local area network is like the bottom line of the internet. Remember, the internet is a connection of networks. So the local area net is a small network. As small as maybe relative, but it's not, when we want to have larger networks, we talk about WANs, WAN, wide area networks, or even MANs, metropolitan area networks. But we're looking at the local area networks. In the LAN, usually everybody, all the networks are for one group. And in there, each of the Ethernet chips has its own address. So now, besides talking about IP addresses that we were talked about and the different forms of them, we now have a new address to talk about. The Media Access Control Address, the MAC address. This means basically that if we're working only within our local area network, we don't necessarily need the IP addresses. The way MAC works is when an Ethernet chip is produced, the company stamps it with a unique address, puts it into the chip. It gets these addresses in the way that each company that creates these gets a set of addresses at the top. The top part of the address refers to the company, and the rest of the address is a unique number for the chip. Now, I did ipconfig/all to see what I had over here, and it's quite complicated because there's many different kinds of adapters involved. But if you look here for my wireless LAN adapter, my physical address is 82 blah 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 blah. My Ethernet adapter has another physical address. So there's lots of different adapters that work with different items here. And you'll notice some of them are disconnected. So I'm not working with them. The ones that are not disconnected, you'll see they're here. I've got my physical address here and lots of other things that we can talk about later. So you might want to look at that on yours and see what you get. Might be interesting to see. So, the problem with wireless lines is they have a lot of errors in them. They're under attack, essentially. Remember, they're not protected. And even the protected lines in wires get errors. So layer 2 is full of error checking. There are many ingenious methods used to detect errors in the transmissions we send. And that's going to be the first thing we're going to talk about at this layer. Now, the layer also does congestion control between neighbors to try to avoid bottlenecks, slow down if necessary, things like that. We saw a little of that up at the network layer. but we'll see more of it down here. The data link layer, as I said, is often done by an Ethernet chip. A chip is between software and hardware. It's sometimes called software burned into hardware. And the important thing about firmware is that it works at the speed of hardware, not at the speed of software. Of course, the disadvantage is that it's burned into the chip, so you're not going to go in and spend some time modifying it. So let's talk about error detection. The easiest error detection is one that I think you've probably already seen. It's called the parity bit. What it is we take a group of bits and we add one bit to it. And the one bit we add is added so that the number of ones is even. That would be even parity. Or so that the number of ones is odd. That would be odd parity. So let's look at odd parity. Suppose we are sending over here the messages to send. Our messages, let's say, are 7-bit. Now, the 7-bit was the old ASCII codes, and we can still look at it as 7 bits we're sending in a bit, in a 8-bit byte, or we could have 15 bits, whatever. The idea is that we need to add something to them so that we will be able to detect a 1-bit change. That's all the parity bit does. If you're going to send this, let's say we're using odd parity, we just append a 0 to what we sent. This one starts out with 4 ones and 2 zeros. We're going to add a 0 to get ourselves, I wanted the number of ones. I don't know why I did this particular way. Let's see. We need the number of ones to be odd. So I will put a 1 there instead. Now I have 5 ones. I have 2 here, so I need a 1. I have 2 here, I need a 1. I have 2 here. I have 3 there, so that's okay. I have 4 there, so I need a 1. I have 3 ones there. I need another 1. So I don't know why I just missed 2 of them. Seems kind of strange. Oh, I was right on this one. There are 3 ones there. Let me look at this other one. I correct it. 1, 2, 3, 4, 5. Yeah. Should have left it alone. They were correct. Now, that's called horizontal redundancy check. It's a fancy name. It just means that for each bit we send, each byte we send, we add 1 bit to make sure that the number of ones in this case is an odd number. What that does is, let's say that this bit here got flipped. It became a 0. Then because it became a 0, the number of ones is now even in this byte, and we know that some bit changed. We don't know which one. So this is only a very simple check. Errors tend to occur in bits, in bursts, so this isn't the greatest in the world. This method detects a 1-bit flip, a 3-bit flip, and so on. If 4 bits flip, we're not detecting them. And we don't know which one. We do not know which bit changed. All we have, if we're doing an HRC and we get the wrong parity, we would send a message back to the sender saying this is a garbled message. We can't read the message, and the sender would be responsible for resending it. One thing you should notice is the cost of this. There are 7 bits of message and 1 bit checking it. So we're talking about 1/8 of our bandwidth is being used to check things. Now, that's minor compared to what's coming. Or perhaps, I think so. The problem that we have is that when a bit gets flipped, usually the bits around it are more subject to being flipped. That makes sense. If there's a disturbance in the electrical interference, it's likely to affect a few bits near one another, next to one another. It's not likely to be totally, if it affects bit X, it's not a totally random whether or not it's going to affect bit X plus 1. It's a physical time that disturbance happens, and the next bit might be within that time. So the horizontal redundancy check does not work for burst. So what can we do? Well, people have decided, let's add another redundancy check. We'll call it the vertical redundancy check. And this time what we'll do is we'll add an extra byte to the group. And now we want the parity in the columns to be the same. So this is the messages we sent, and they have their HRC already. And then in each column we look and say we want to have an odd number of zeros. 1, 2, 3, 4, 5. Well, just put a 1 in. 1, 2, oh, we better put a 0 in to get 3. 1, 2, 3, 4, 5. That's okay. 1, 2, 3, 4. We need a 0, and so on. So again, 1/8 more of the bandwidth. I guess in this case it'd be 1/9 if we decide to 1, 2, 3, 4, 5, 6, 7. It's 1/8. It doesn't have to be 8. We could go with a larger number. All right. That gives us some help. It lets us detect some burst and a single bit or a number of bits changing. It's by far not the best we can do. Now, there's several possibilities. One of the more interesting possibilities is the idea of using theory from mathematics, polynomial theory, to decide how to put in check bits. And this is called the cyclic redundancy check. Now, it'll look a little strange at first, but it's not very difficult if you ignore trying to prove it works. That's the job of the mathematicians at this point. The way we allow ourselves to use the theory is that we have to think about this group of bits we're sending as the coefficients of a polynomial. But the polynomial is a strange polynomial. It's over what's called the field of 0 and 1. In other words, the x in it can only have values 0 and 1. And the coefficients can only have values 0 and 1. And we have a little different arithmetic in this particular field we're working with. The arithmetic is the exclusive OR. 0 plus 0 is 0, 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1. Think of it as you have to have 1 in order to have 1 in the answer. You've got to have exactly 1. You can think of 1 as true and 0 as false, for example. There's no carry. It's bit by bit. We're not carrying over. It's not as if 1 plus 1 is 0 and carry a 1. It's 0, period. The next bit isn't affected. So we're going to use something called cyclic redundancy check sum, CRC. We start with a message we want to send. Now, my messages are going to be kind of small because I don't feel like doing an awful lot of arithmetic. So I'm sending the message 1001011. Starting on the right, I'm looking at powers of x. So x0 has a coefficient of 1. X to the 1 has a coefficient of 1. X squared has a coefficient of 0. X cubed has a coefficient of 1. X to the 4th has a coefficient of 0. X to the 5th has a coefficient of 0. X to the 6th has a coefficient of 6. This is a degree 6 polynomial, but there are 7 digits here, because remember we start at 0. Now, that's just a convenience so that we can invoke the theory. Once we write the program for it, we don't have to think much about the theory anymore. The program, if we want to prove the program works, or properties of the program, that's when we have to resort to the theory. So, we're going to choose another polynomial C of degree n. Now, I'm choosing a very small one. I'm choosing x cubed plus x plus 1. The degree is n, and I believe the rule is that it has to end in a 1. There are some there are standard polynomials that are used, and they're not for degree 3. They're degree 16, 32, 64, things like that. Much larger than we have here. But this will give us a chance to look at it. Now, this is a nth degree polynomial. The first step in creating what we send is to multiply what we want to send, which is d, times x to the n. Now that's very, very easy. All it amounts to is adding n to each of the exponents. So we have a degree 3 multiplied by x cubed. That means we take the, I got to be careful how I did this. It's sad that I didn't get the pot there, but it'll work. We multiply the x cubed times the message we want to send. X cubed times x to the 6th is x to the 9th. X cubed times x cubed is x sixth. X cubed times x is x4. X cubed times 1 is x cubed. Remember, when we multiply, we add the exponents. So this represents another bit. We can look at it. We have no zeros, no ones, no twos, a 1, a 4, no 5s, a 6, a 7, an 8, and a 9, a 1, 9. In all practicality, all you're doing is adding 3 zeros to the right-hand side. That's all it is. And that's a shift. So it's very fast to do that. But again, look, this was a degree 3 polynomial. And the result of doing it was to put 3 zeros on the right-hand side of what we're sending. Now, we're going to do a division. What we're going to do is we're going to divide this and get a remainder. Then we're going to take that remainder and add it back in. When we do that, that means that when the other side does the division by the polynomial c, it should not get a remainder. If it gets a remainder, there's something wrong with what we are sending. So that's the theory, the idea behind this. So what do? We're going to divide what we just got there by the c. Now, watch out for division here. Division is extremely simple in some sense. One item divides into another item if they're the same length or greater length. 1011 divides 1001. It wouldn't in the real world that we have been living in our arithmetic, but it does in this XOR arithmetic. What it says is, if you're dividing by a polynomial of degree 3, you need 4 coefficients before you can say that this divides into that. So this divides into the first part here as a 1. Then we do a simple multiplication as we do in long division in our way. 1 times 1011 is 1011. And now we do a subtraction. And the subtraction is the XOR subtraction. So when we subtract 1 from 1, we get a 0. 1 from 0 is a 1. And 0 from 0 is 0. And 1 from 1 is 0. Remember, if you look at this, the 1 and the 0 here add to 1. The 1 and the 1 here add to 0. So that's why the subtraction works there. Now we bring down the next 0. Bring down the 1. Now we have 4 digits again. So our polynomial that we're dividing by divides into it. Same thing. Bring the 1 down. 1011. Now do the same subtraction method that I used. Now we have to bring down the next 10. We do the work there. We bring down the 2 zeros. We can't divide. It's not long enough. The numerator and the division isn't long enough. So there's our remainder. It's 100. Now what do we do with the remainder? We add it in. Now, adding it in is going to be very easy. It's just going to be, basically it's going into the end, the last 3 digits there. Because the remainder has to be less than 4 places. Because remember, we're dividing by, if it were 4 places, we could do a division. So the remainder has to be 0 digits, 1 digit, or 2 digits, or 3 digits. It can't be more than that. Excuse me, I've got a visitor who is deciding she wants to be part of the show here. So I'm sorry. Now, we are sending a item that the other side knows our C. So what does it do? When it gets the message, it divides by C, and it looks at what its remainder is. If its remainder is 0, something went wrong. I mean, if its remainder is not 0, something went wrong. If its remainder is 0, we can't guarantee you everything is perfect, because there are some things that this will not detect. But the theory tells us there's a tremendous number of things it will detect. Now, I told you that I'm using 4 digits here for my sample. I didn't want to use any of these. I told you they were kind of large. The CRC 16 is there. There's an 8. Look at the Ethernet one. It's a polynomial degree 32. I didn't feel like going through that. I thought it might be a little bit of work for us to do that. But you can see that there's a lot of standard ones that are used. Now, that I think will get us started, and I'll do the error correcting code on the next video. So we'll see you later, and if I don't see you before the weekend, have a nice Easter and Passover,